Usually when we talk about navigating our world, there is a physical reality to it. You
Oh,
know,
absolutely.
like you look at a map, you see a highway, a river, a mountain range. It is completely tangible.
Right.
But when you step into the world of modern aviation, into the flight deck of a commercial airliner, that physical reality just vanishes.
Yeah, it really does.
I mean, we are flying these 300-ton aircraft along invisible, mathematically perfect digital corridors that only exist inside a computer's database.
It is entirely abstract. We basically replaced concrete landmarks with computed performance specifications.
Yeah.
We are trusting our lives and the lives of hundreds of passengers to signals bouncing off the ionosphere and to the, microscopic ticking of atomic clocks floating 20,000 kilometers out in space.
And what's wild is that to get the license to fly those modern digital corridors,
Yeah.
you still have to prove you can navigate using technology developed in the 1950s.
Oh, heavily, yes.
I am sitting here looking at a massive stack of documents on my desk. I've got ESA regulatory updates, the newly released ECQB 2026 syllabus changes, and pages of intellectual property protected question banks.
Right. The stuff they don't want you to see.
Yeah, exactly. And we've spent weeks distilling this down to the absolute essentials.
Yeah.
So our mission for this deep dive is to conquer the airline transport pilot license, the ATPL radio navigation, and performance-based navigation syllabus.
A huge undertaking.
It is. We are going to make sense of the nervous system of modern aviation, so anyone facing these exams is completely prepared.
And I have to say, this is a critical moment for anyone preparing for these exams.
So.
Because understanding what is actually in the syllabus, and just as importantly, what isn't, is the difference between passing and failing right now.
Yeah, that makes sense.
The European Central Question Bank, the ECQB, it contains roughly 10,000 questions, and it is strictly confidential.
It's totally locked down.
Right. Those commercial question banks students might be studying from, they are just guessing based on candidate feedback. They don't have the actual master key.
Which means you cannot just memorize the answers anymore. I mean, you have to genuinely understand the underlying mechanics.
Exactly.
And the landscape of the syllabus itself is really fractured right now. If I'm a student pilot, I might be getting pulled in different directions depending on, where I live.
Yeah, the regulatory landscape is very divided. If you are sitting your exams with EASA or the UK CAA, you're facing what's called the new syllabus.
Okay, the new one.
Right. This is based on the 2018 and 2020 learning objectives, which have been continually updated through ECQB 2021, 2022, 2024, and now the ECQB 2026 update that just went live in August.
Okay, so that's EASA and the UK. What about everyone else?
Well, if you are in other ESA-compliant states, places like Hong Kong, the Gulf, or South Africa, you are still being tested on the old syllabus, which relies on the 2016 learning objectives.
Wow. So if I'm bouncing between my flight school, my ATO, and my national authority, say Controller FOCA in Switzerland, how am I supposed to keep up with these rolling timeline changes?
It's tough.
Like, what if my school is teaching one thing, but the exam expects another?
That is actually the single biggest trap for students today. You absolutely must explicitly confirm the transition timeline with your ATO.
Yeah.
Look at the fascinating quirk in the ECQB 2024 update, for example.
What had in there?
The authorities actually removed older all-weather operations or AWOT-PS minima questions.
Wait, really? Just completely remove them?
Yeah, because they didn't align with the 2021 and 2022 rule changes. So if you were studying from an outdated manual, you were burning mental energy memorizing highly complex minima calculations that were no longer even on the test.
Oh man, that is a brutal way to waste study time.
It really is.
Let's make sure we are completely up to date then. What are the big headline changes for this new ECQB 2026 syllabus that is active right now?
So they are evolutionary but highly specific to modern challenges. In air law and communications, there is a brand new squawk code, 7601.
Oh, do a new squawk code.
Yes. This is specifically and exclusively for an IFR in VMC communication failure.
Okay, let me break that down to make sure I've got it. I am flying under Instrument Flight Rules IFR.
Right.
But the weather outside is clear, so I am in visual meteorological conditions VMC.
Exactly.
Suddenly my radios die, I squawk 76001. Basically, I'm telling air traffic control, I have lost comms, but don't panic, I can see where I'm going.
That is the exact message.
Nice.
And speaking of communication failures, they have extended the timing rule in a radar environment.
How much?
It used to be 7 minutes before you proceed according to your flight plan. It is now 20 minutes.
Oh, wow, that's a huge jump.
Yeah.
Hmm.
And moving over to meteorology, the World Area Forecast Center T plus 24 significant weather charts, the ICWX charts, are now fully colored.
Finally.
Right. They feature new specific annotations for turbulence and icing, and there is entirely new test material on the impacts of climate change on aviation operations.
That makes sense. The environment is shifting, so the exam shifts to reflect that reality.
Mm-hmm.
What about the human element in flight planning?
Flight planning has seen modernized calculation procedures for contingency and discretionary fuel management.
Which aligns with real-world flying, right?
Exactly, aligning with how modern airlines actually operate today.
Good.
And in human performance, there is a massively expanded emphasis on fatigue risk management.
Also very needed.
Definitely. And looking at future airspace, the syllabus now heavily tests use-based regulations and drone integration.
The airspace is getting exponentially more crowded. I mean, the rules are getting tighter, and the navigation is getting incredibly digital.
It is.
But before we get to the space-age digital stuff, the PBN, we really have to build the resilient foundation.
We do.
We need to talk about conventional ground-based navigation, because even in 2026, the exam is obsessed with the VOR.
Oh, absolutely obsessed. And for good reason.
Why is that?
The VHF omnidirectional range, the VOR, is tested so heavily because it is the ultimate safety net. It is what we fall back on when GNSS, our satellite navigation, is jammed or fails entirely.
Which is happening more and more.
Exactly. With intentional signal jamming increasing globally, authorities are terrified of a scenario where screens go dark and pilots don't know how to fly the physical beacons.
That would be a nightmare. Let's get into the mechanical guts of the VOR then.
Sure.
It operates in the VHF band, specifically between 108.0 and 117.975 megahertz.
Yep.
But there is a classic trick built into those frequencies that trips people up on the exam.
Yes, the frequency allocation trick.
Yep.
Any frequency between 108.0 and 111.975 that has an odd number in the first decimal place is reserved exclusively for the Instrument Landing System, the ILS.
So like 109.1 or 109.3 would be ILS?
Correct. But 109.2 or 109.4 could be a VOR.
Okay, I see.
You also need to keep in mind that 8S, the Automatic Terminal Information Service broadcasting local airport weather, is often transmitted piggybacked on VOR frequencies.
Okay, got it. Now, I've always struggled to visualize how a VOR actually tells an airplane where it is in the sky.
It can be tricky to picture.
The best way I've found to understand it is the lighthouse analogy.
Oh, I like that one.
Yeah, so imagine a lighthouse that shoots a continuous pulsating green light in all directions.
Okay.
But it also has a highly concentrated, sweeping white beam that rotates clockwise, like a searchlight.
That analogy perfectly explains the phase difference principle the VOR relies on.
Really? How does it map out?
Well, the VOR transmits two distinct signals. First is the reference signal.
Okay.
This is an amplitude modulated, or AM, signal transmitted on the main carrier wave. It pulses exactly when that sweeping beam passes magnetic north.
So that is my pulsating green light.
Exactly. And the sweeping white beam, that is the veriphase signal.
Which is different from AM.
Right. It is frequency modulated, FM, transmitted on a subcarrier.
Oh, okay.
Your aircraft receiver is essentially standing in the dark watching this lighthouse. It sees the green flash of the reference AM signal, starts a microscopic timer, and stops the timer when the sweeping white beam of the veriphase FM signal hits it.
And by doing that,
By measuring the phase difference between those two signals, the receiver calculates exactly which radial you are on.
that is brilliant. But the syllabus distinguishes between two types of VORs, right?
Yes, does.
There's the conventional one, the CVOR, which actually has a physical rotating antenna inside that giant white bowling pin structure we see at airports.
Right.
And then there's the modern one, the Doppler VOR or DVOR.
Yes. The CVOR has a fatal flaw. It is prone to something called scalloping.
Scalloping, like the potato dish.
Kinda, but worse for navigation. The radio signals bounce off nearby terrain, buildings, or even taxiing aircraft, causing the radials to bend and warp.
Oh, so your needle in the cockpit will just wave back and forth.
Exactly. It's not a clean line.
Yeah.
The DVOR fixes this elegantly.
How does it do that?
It uses a massive ring of 50 fixed antennas and utilizes the Doppler shift principle to simulate the rotation electronically with zero moving parts.
Oh, why?
It provides a vastly cleaner, more stable signal.
Wait, if the ground equipment is so fundamentally different, like a spinning physical antenna versus 50 fixed electronic antennas, does the airplane need a different kind of radio to talk to a DVOR?
That is a crucial trap for the exam.
Okay.
The answer is no. Your aircraft receiver does not care.
Oh, really?
The brilliant engineering behind the DVOR is that it creates a signal that is mathematically indistinguishable from a CVOR. The airplane reads both in exactly the same way.
Which brings us back to the lighthouse analogy.
Exactly.
If I am standing out at sea looking at a lighthouse, it doesn't matter which way my boat is facing.
Nope.
I could be driving toward the lighthouse, or I could be driving away from it. I am still standing on the same physical line of bearing from the beacon.
That's right.
The VOR course deviation indicator, the CDI, works exactly like that.
No.
The indication on the instrument is entirely independent of the aircraft's heading. It only cares about geometry.
And that single geometric concept is the foundation of one of the most notoriously tricky exam questions.
Oh, the examiners love this one.
They really do. They love to test if you truly understand that your aircraft's heading is utterly irrelevant to the needle's position on a traditional VOR indicator.
Okay, let's walk through this specific exam scenario, because this destroys people's confidence. I call it the reciprocal trick.
Name for it.
So, the exam gives you this setup. Your aircraft is flying on a magnetic heading of 300 degrees. You are physically located on radial 120.
Okay.
The pilot sets the OBS, the Omni Bearing Selector, to 330. What does the CDI needle indicate?
Right. So the first rule of this question is to actively ignore the aircraft's heading for the geometric calculation.
Just cross it out.
Literally, the heading of 300 is only there to help you visualize the direction of travel. Let's methodically map it out.
Okay.
If you are on radial 120, you are to the southeast of the VOR station.
Yeah.
And a heading of 300 is the exact mathematical reciprocal of 120. This means your aircraft is pointing northwest, flying directly along the 120 radial, straight towards the station.
Okay, slow down. My brain is twisting in knots.
Take your time.
Let me draw this out on my mental whiteboard. I'm southeast of the beacon. My nose is pointing at the beacon. I'm flying inbound.
Right. Now look at the instrument. You have selected 330 on the OBS.
Okay.
The OBS defines your desired path. Because you are flying towards the station, the radial you actually want to be on to fly an inbound course of 330 is the reciprocal of 330.
So 330 minus 180 is 150. I want to be physically sitting on radial 150.
Precisely. Your desired position is radial 150. Your actual current position is radial 120.
Okay, I have those two numbers.
Now, visualize the compass rose drawn on the ground around the VOR.
Yep.
If you are sitting on the 120 line, where is the 150 line? It is 30 degrees further clockwise around the circle.
Okay, I am on 120, looking towards the center of the circle on my heading of 300. Radial 150 is clockwise from my position, which means from my perspective in the cockpit, the 150 radial is physically off to my left.
Perfect. Therefore, to get from your current location on the 120 radial over to your desired location on the 150 radial, you must physically fly the aircraft to the left.
So the needle says fly left.
The CDI needle will indicate fly left.
That is deeply counterintuitive until you draw it out.
It really is. And just to add to the instrument knowledge, a standard VOR indicator has a 5-dot scale, and each dot represents 2 degrees of deviation.
Oh, so 30 degrees is way off.
Yeah, a 30-degree difference is completely off the scale. The needle will be pinned to the left wall of the instrument case.
Right.
Exam questions often simplify the math. If the question asked for a 4-degree difference, it would be a 2-dot deflection. But the core action is fly left.
The lesson there is to always draw it out on scratch paper. Do not try to hold those rotating compass wheels in your head.
Never try to do it in your head.
Now, a VOR is great, but it just gives you a single line. It doesn't tell you how far away the lighthouse is. For that, we need DME distance measuring equipment.
Exactly. DME operates in the UHF band, and it works on a fundamentally different principle than radar.
How so?
Well, radar sends out a pulse and waits for it to bounce off a passive object. With DME, the aircraft is the active interrogator, and the ground station is an active transponder.
Oh, so they are talking to each other.
Right. The aircraft sends out a paired pulse, the ground station receives it, pauses for a highly calibrated 50 microseconds, and transmits a reply.
Why the pause?
Just processing time. The aircraft measures the total time for the round trip, subtracts that 50 microsecond delay, and mathematically calculates the distance.
But it's calculating slant range, right?
Yes, exactly.
It's giving you the hypotenuse of the triangle formed by the ground station, the point on the ground directly below your aircraft, and your altitude.
Slant range creates a fascinating quirk on the exam.
I know this one.
Go ahead.
If you fly directly over a DME ground station at an altitude of 6,000 feet, your DME instrument will not read 0 miles.
Yep.
It will read approximately 1 nautical mile because you are physically 1 nautical mile straight up in the air from the antenna.
Spot on. And unlike a VOR, where infinite people can look at the lighthouse, DME has a hard capacity limit.
Right, because it's actively talking to each plane.
A VOR just blindly broadcasts the signal, but a DME ground station has to actively process, calculate, and transmit a reply to each individual aircraft interrogating it.
That takes processing power.
Exactly. It is limited by its processing power and transmitter duty cycle. It can only handle a maximum of 100 aircraft at a single time.
So what happens when aircraft 101 tries to get a distance? Does the whole thing crash?
Fortunately, no. The ground station will start dropping the weakest signals to protect itself from overloading.
Ah, smart.
It prioritizes the strongest interrogations, which almost always means the aircraft physically closest to the station keep their distance readouts.
Now the guy's further out.
Aircraft further away on the edge of coverage simply see their DME screens go blank.
Brutal, but necessary. There was another exam favorite regarding DME, the DME arc. Air traffic control tells you to fly a massive perfect circle around the station at, say, a distance of 15 miles. What happens to your ground speed readout on the DME instrument while you are flying that arc?
The DME computer calculates ground speed by measuring the rate of change in your distance to the station over time.
Right.
If you are flying a perfect arc, your distance to the station is not changing. It stays locked at exactly 15 miles.
The math just zeroes out.
Exactly. Because the rate of change is zero, your DME ground speed readout will drop to 0 knots, even if you are flying at 250 knots through the air.
It's such a good trick question. So VOR and DME are fantastic, but they require line of sight. They don't work through mountains.
They do not.
They are expensive to install. What happens when you're flying in remote terrain, deep valleys, or developing nations where that infrastructure just doesn't exist?
You fall back on the oldest, most stubborn tech in the syllabus, the NDB, the non-directional beacon.
They are ancient.
Very. Operating in the low and medium frequency bands, but they are still tested.
What does the exam focus on for NDBs?
The exam specifically zeroes in on the tolerances required to be considered established on an approach.
And being established is critical for obstacle clearance, right?
Absolutely. It means you are officially within the protected airspace corridor and won't hit a mountain. To be considered established on an NDB approach, your bearing pointer must be within plus or minus 5 degrees of the required track.
And how does that compare to a VOR or a localizer approach?
The tolerances are much tighter for the newer tech. For a VOR or localizer, you must be within half-scale deflection on your instrument.
Got it. You also need to know how to identify these nav aids on a chart.
Yes.
An NDB is shown as a cluster of small dots with a 3-letter frequency. A VOR uses a Morse code identifier, and on a modern JSON chart, if the VOR is co-located with a DME, it will have a small letter D tucked next to the icon.
That brings us to the absolute pinnacle of ground-based navigation. The ILS, the Instrument Landing System.
The system that saves lives every day.
Truly. This is the technology that safely guides airliners down to the runway through thick fog and blinding snow. It consists of 3 primary components: the localizer for lateral left-right guidance, the glide path for vertical up-down guidance, and marker beacons or a DME for range information.
The localizer uses VHF frequencies, just like the VOR, but the glide path uses UHF. How does the aircraft actually know if it's perfectly centered on that invisible runway line?
The system relies on a physical principle called difference in depth modulation, or DDM.
Difference in depth modulation.
Yes. The ground transmitter at the far end of the runway sends out 2 overlapping, highly directional radio lobes down the runway centerline.
Okay.
The radio lobe on the left side of the centerline is modulated at 90 hertz. The lobe on the right side is modulated at 150 hertz.
I picture like 2 overlapping cones of colored light.
That's a great way to view it.
So the left side is tinted blue, the 90 hertz, and the right side is tinted red, the 150 hertz. If I stray too far left, my receiver hears more of the blue, the 90 hertz signal. If I drift right, it gets dominated by the red, the 150 hertz signal.
The aircraft's receiver constantly measures the difference between those 2 modulations. When you are flying perfectly down the center line, the signal strength of the 90 hertz and 150 hertz lobes are exactly equal.
So they cancel each other out.
Basically. The difference between them is 0. When the DDM is 0, your localizer needle sits dead center.
And the glide path.
The glide path works on the exact same DDM principle. It is just flipped horizontally. The 90 hertz lobe is projected above the glide path, and the 150 hertz lobe is projected below it.
The syllabus makes a massive point about the sensitivities between the localizer and the glide slope, though. They are vastly different.
They have to be. The localizer is less sensitive. It requires a 2.5-degree deviation either side of the center line to reach full-scale deflection on your instrument.
Which gives you a fairly wide funnel, right?
Yes, the localizer signal gives you a wide funnel of coverage out to 25 nautical miles, provided you are within 10 degrees of the center line, and it reaches 17 nautical miles if you are out to 35 degrees.
But the glide slope is an entirely different beast.
The glide slope is highly sensitive. It only takes a tiny 0.7-degree deviation to reach full-scale deflection.
Wow, less than a degree.
And its coverage area is much shorter and narrower. It only reaches 10 nautical miles and only covers 8 degrees either side of the center line.
Let's translate those degrees into what the pilot actually sees on the cockpit instruments, just to make it real.
Sure.
On a standard 5-dot horizontal situation indicator, an HSI, 1 dot of deviation on the localizer equals 0.5 degrees.
Right.
But one single dot on the glide slope is an incredibly tight 0.14 degrees. You cannot casually hand fly a glide slope. You really have to fly it with intense precision.
Which is why we rely so heavily on automated flight control systems for low visibility operations.
Seriously.
Now, while we are talking about radio waves connecting the plane to the ground, we have to talk about how air traffic control actually sees us. We need to cover transponders and radar.
I love the transponder math in the syllabus. Transponders work on the octal numbering system, meaning they only use digits 0 through 7.
Do you know why they use the octal system?
Is it a computer thing?
It traces back to the physical hardware of early transponders. They used three 3-bit binary dials. Mathematically, 3 bits can only produce 8 possible combinations, the numbers 0 through 7.
Oh.
The numbers 8 and 9 literally could not exist on the physical hardware dials.
So when you get an exam question asking to identify an invalid transponder code out of a multiple choice list, you just scan the numbers looking for an 8 or a 9.
That's the trick.
There are 4,096 possible combinations in the octal system, but the number 4096 is itself an invalid code because it contains a 9.
Exactly. A code like 5D600, however, is perfectly valid because it only uses digits 0 through 7.
That is so simple once you know the history.
Now, there are 3 main modes of transponders we need to know: Mode Alpha, Mode Charlie, and Mode Sierra.
Okay.
Alpha provides basic identification. Charlie provides altitude, but it is limited to 100-foot increments.
And Mode Sierra Mode S is the modern standard.
Mode S provides altitude in 25-foot increments.
That's pretty precise.
This level of precision is absolutely required for TCAS, the Traffic Collision Avoidance System, to issue resolution advisories.
Oh, because of the closing speeds.
Right. If TCS is going to take over and command one airliner to climb and another to descend to avoid a mid-air collision at closing speeds of 1,000 miles an hour, it needs that 25-foot accuracy to calculate a safe escape trajectory.
The transponder receives interrogations from the ATC radar on 1030 megahertz and replies on 1090 megahertz. But the radar environment isn't perfect, is it?
No, not at all. The syllabus highlights 2 specific errors: garbling and fruiting.
They sound ridiculous, but the concepts are serious.
Garbling occurs due to physical proximity. When 2 aircraft are flying in the same direction, less than 1.7 nautical miles apart, their transponder replies physically overlap in the air.
Just crashing into each other.
Exactly. The radios crash into each other, creating a garbled, unreadable signal by the time it reaches the ATC antenna on the ground.
And
Fruiting is a network issue. It happens when an ATC radar receives a perfectly valid transponder response, but that response was actually triggered by an interrogation from a completely different ATC station in the region.
so it's basically eavesdropping on someone else's conversation.
Yeah, and it creates random clutter on the radar screen. Modern ATC systems use a software process cleverly called defruiting to filter out those random, unsynchronized responses.
While we're talking about radar, we have to mention airborne weather radar.
Very important.
This isn't for ATC. This is the radar dish swinging back and forth in the nose of the plane for the pilots. The syllabus states it operates on a 3-centimeter wavelength. Why exactly 3 centimeters?
Because in radar physics, the wavelength must match the physical size of the object you are trying to detect.
Oh, I see.
3 centimeters is the optimal wavelength to reflect off large, wet precipitation, specifically wet hailstones and heavy rain.
Makes sense.
It uses a narrow, concentrated, cone-shaped beam about 3 to 5 degrees wide. You have to constantly tilt this beam up and down to scan different altitudes of the storm structure.
But there is a massive warning in the syllabus about the shadow area.
This is critical for safety.
Let me picture this. I'm flying at night, painting a massive, intense thunderstorm on my radar. The screen shows a wall of red and magenta directly ahead.
Right, so the heavy rain and hail at the front edge of that storm cell are so dense that they absorb or scatter all of the radar's energy.
Okay.
This means the radar waves simply cannot penetrate through to the back of the storm. The area behind that initial wall of heavy rain will look completely black and clear on your screen.
Wow. But it's not clear.
No, in reality, it could be hiding an even more violent supercell. That is the shadow area.
So if I try to navigate around the red blob by flying into the black area behind it, I could be flying directly into the most catastrophic part of the storm.
Yes, you have to constantly manage your antenna tilt and understand that absence of an echo does not always mean clear air.
That is terrifying.
Okay.
The last piece of the conventional puzzle.
Yeah.
Communications. VHF versus HF.
VHF, very high frequency, is strictly line of sight. The radio energy propagates as ground waves and is generally limited to about 150 to 200 nautical miles, depending on the altitude of your aircraft.
But if I am flying an A330 across the North Atlantic, 200 miles isn't going to cut it. I need HF high frequency.
HF is historically used for long-haul meteorological information like VOLMIT broadcasts.
Why does it go further?
Because HF operates at a much lower frequency, the radio waves can actually bounce off the Earth's ionosphere as sky waves.
Oh, wow.
They refract back down to Earth, allowing the signal to travel far over the horizon, reaching distances up to 1,000 nautical miles or more.
I remember listening to those HF radios. They are incredibly crackly and full of static.
Very noisy.
To make HF more efficient, the syllabus requires us to understand single sideband, or SSB. If I remember my high school physics, a standard radio transmission creates a carrier wave and two identical sidebands that carry the actual audio information, mirroring each other above and below the carrier.
Right. SSB literally slices the signal apart. It strips away the carrier wave and deletes one of the mirrored sidebands before transmission.
So you're only transmitting half the way.
Exactly. By doing that, you save 50% of the transmission energy. You dedicate all your transmitter power to a single sideband containing the essential audio.
That's incredibly efficient.
It is. This massively increases the range and clarity of the signal, which is vital when you were trying to decipher a weather report halfway across the ocean.
We have this vast, incredible network of ground-based VORs, DMEs, and radars. But they all share massive limitations.
I do.
They're blocked by mountains, limited by the curvature of the Earth, they run out of capacity, and they require expensive ground stations.
And constant maintenance.
It's exactly. To navigate globally, over oceans and polar ice caps, with absolute continuous precision, aviation had to look up. We had to look to the stars.
And the global transition to space-based navigation, to GNSS, was actually catalyzed by a profound tragedy.
September 1st, 1983. Korean Airlines Flight 007, a Boeing 747 flying from New York to Seoul.
The crew made a subtle but critical error during departure. They failed to properly engage their inertial navigation system, their INS.
Oh no.
As a result, the autopilot simply flew a constant magnetic heading for hours through the night.
It's just drifting.
Unbeknownst to the crew, they drifted hundreds of miles off their intended oceanic track, straying deep into highly restricted Russian airspace over the Kamchatka Peninsula.
And they were intercepted.
Yes. The aircraft was intercepted and shot down by a Soviet fighter jet. All 269 people on board died.
It was a global geopolitical crisis, and it forced a massive technological paradigm shift.
At the time, the Global Positioning System, GPS, was a highly classified U.S. military project.
Right.
In the direct aftermath of KL-007, the Reagan administration announced that once the GPS network was fully operational, it would be opened up for civilian aviation use globally, completely free of charge.
To make sure it never happened again.
The goal was exactly that, to ensure a navigational error of that magnitude could never happen again.
So how does GNSS Global Navigation Satellite System actually tell an airplane where it is?
Yeah.
It is not like radar. The satellites are not pinging the plane and listening for a bounce.
No, it is a completely passive system on the aircraft's end. The satellites are essentially just highly accurate flying clocks.
Flying clocks.
Each satellite has an atomic clock on board, and it constantly broadcasts a continuous radio signal that essentially says, here is exactly where I am in space, and here's the exact microsecond I sent this message.
So my aircraft receiver catches that signal, notes the exact time it arrived, and figures out how long the signal took to travel from space.
Precisely.
Since radio waves travel at a constant speed, the speed of light time equals distance.
That initial distance calculation is called pseudo-range.
Why pseudo?
It is called pseudo-range because it is not perfectly accurate yet. Your aircraft receiver does not have a multi-million-dollar atomic clock. It has a relatively cheap quartz clock, much like a wristwatch.
Ah, right.
Therefore, your receiver's time is slightly out of sync with the satellite's perfect time.
Which means the distance calculation is slightly off. How do we solve for that timing error?
By adding more satellites into the mathematical equation, the navigation system has 4 unknown parameters that it needs to solve for: your x, y, and z, physical coordinates, latitude, longitude, and altitude, and a variable called delta t, which represents the clock error in your receiver.
4 variables.
Because there are 4 unknown variables, you need exactly 4 satellites to compute a 3D position fix and to synchronize your receiver's quartz clock with the atomic clocks in space.
4 satellites for a 3D fix. That is a foundational exam number. But even with 4 satellites locked in, the system isn't flawless. There are physics-based errors we have to account for.
The total error of the system is calculated by combining 2 factors: the user equivalent range error, UERR, with the geometric dilution of precision, GDOP.
GDOP, what's that?
GDOP simply relates to the physical geometry of the satellites in the sky above you. If all 4 satellites are clustered tightly together in one corner of the sky, the geometry is poor, the triangulation is weak, and the error multiplies.
So you want them spread out.
Exactly. You want the satellites spread out widely across the horizon.
What about the user equivalent range error? What is physically causing that?
The single most significant error in the U-error equation is ionospheric propagation delay, or IPD.
Ionospheric delay.
Okay.
As the satellite signals pass through the Earth's ionosphere, the dense layer of charged particles acts like a refractive medium. It physically slows the radio signal down.
Oh.
Because the receiver relies on the speed of light being perfectly constant to calculate distance, this microscopic delay introduces a massive position error.
How on earth do we fix a delay caused by the atmosphere? You can reduce it by using mathematical modeling, guessing what the delay might be based on time of day. But the most effective way to eliminate IPD is by using dual-frequency receivers.
How do those work?
Different radio frequencies are delayed by the ionosphere by slightly different amounts. By comparing the arrival times of 2 different frequencies from the same satellite, the receiver can calculate exactly how much delay the ionosphere is causing at that exact moment and mathematically cancel it out.
That is brilliant engineering. The syllabus mentions a few other smaller errors, like ephemeris errors, which are slight variations in the satellite's physical orbit caused by solar wind or the gravity of the moon, and multipath errors, where the signal bounces off the aircraft's own wing or fuselage before hitting the antenna.
Yes, those are present too.
But here's the kicker. Even if we fix all these errors, basic unaugmented GNSS is still legally not reliable enough for civil aviation.
Not on its own. To rely on satellite technology for civil aviation, the system must meet 4 strict, non-negotiable conditions. Accuracy, availability, meaning the signal must be available 95% of the year with global coverage continuity, meaning the system will not fail during 95% of a given flight operation, and integrity.
Integrity is the massive one.
Integrity is about trust. If a satellite's atomic clock starts drifting or it gets knocked slightly out of orbit by a micrometeorite, it will broadcast bad data.
And the receiver wouldn't know.
With basic unaugmented GPS, it could take up to 4 hours for the ground control stations in Colorado to realize the satellite is faulty, upload a correction, and warn users.
In 4 hours, an airliner could fly across an entire ocean using corrupted navigation data. That is entirely unacceptable.
Completely.
So we have to augment the system to provide integrity. The syllabus focuses on 3 types: GBAS, SBAS, and ABS. Let's start with GBAS, the ground-based augmentation system.
GBS is a highly localized solution. It uses a ground station situated directly at the airport. This ground station precisely knows its own fixed, surveyed location.
So it can compare notes.
Exactly. It receives the GPS signals from space, compares its known location to the GPS calculated location, determines the exact errors in those signals, and broadcasts a real-time correction directly to incoming aircraft via a VHF data link.
Oh, that operates right in that 108 to 118 megahertz band we talked about earlier.
You got it.
The coverage area for GBS is pretty small, only about 20 nautical miles around the airport, but it allows for something incredible: GLS approaches, the GNS landing system.
It's game-changing.
The GBA station transmits a final approach segment, or FAS, data block to the aircraft. This allows the plane to fly a highly precise 3D approach, essentially replicating an ILS, but entirely using satellites.
And this augmentation precision is absolutely vital. The syllabus provides a very sobering mathematical context here.
Yes, I saw this.
Imagine you are flying an approach down to a minimum descent altitude of 200 feet, which is about 60 meters. If your unaugmented GPS has a vertical deviation error of just 15 meters.
Let me stop you there. 15 meters divided by 60 meters, that is 25%. So if I am breaking out of the clouds in a heavy A320, staring at my instruments thinking I have a safe 200 feet of clearance from the ground, a standard unaugmented GPS error could mean I am actually 50 feet lower than I think I am.
Yes.
I could literally be scraping the approach light antennas. That's terrifying.
That is exactly why GBAS is strictly required for localized precision approaches. Now, let's contrast that terminal precision with SBS, the satellite-based augmentation system.
If SBAS uses satellites to fix satellites, and GBAS uses ground stations to fix satellites, why do we need both systems?
Because they serve entirely different flight phases. GBAS is only good for 20 miles around a specific runway. SBS is designed for immense regional and en route integrity.
Okay.
SBS uses a vast network of ground monitor stations spread across an entire continent, systems like WAAS in the US, EGNOS in Europe, GAGAN in India, or MSS in Japan.
I see. So these ground stations monitor the GPS satellites, calculate the errors across the whole continent, and send those corrections up to a separate geostationary satellite parked over the equator. And that geostationary satellite broadcasts the corrections down to the aircraft on a UHF frequency.
The most critical function of the SBS network is not just enhancing accuracy, it is guaranteeing integrity.
Right, the trust factor.
If a GPS satellite starts broadcasting bad data, the widespread SBS network will detect the anomaly and alert every aircraft in the system to ignore that specific satellite within exactly 6 seconds.
From a 4-hour delay down to a 6-second warning. That is the safety margin commercial aviation requires.
It's essential.
Finally, we have ABS, aircraft-based augmentation. This is all handled internally on board the aircraft.
The most common form of AB is RAIN receiver autonomous integrity monitoring. We know we need 4 satellites for a basic 3D fix.
Yeah.
RAIN requires a minimum of 5 satellites in view. The receiver compares the positioning data from all 5 to see if they all mathematically agree.
And if they don't?
If one satellite is giving conflicting data, RAIN detects the fault. But to actually isolate the faulty satellite and exclude it from the navigation solution so you can keep flying safely, RAIN requires 6 satellites in view.
4 to navigate, 5 to check for faults, 6 to isolate the bad one. That is perfect exam material right there. There's also AAM, Aircraft Autonomous Integrity Monitoring.
AAM achieves integrity by cross-checking the satellite data against completely independent onboard sensors like the inertial reference system, the IRS, or the barometric altimeters.
We have established the resilient ground beacons, and we have unpacked the hyper-accurate augmented satellites. Section 4 of the syllabus is where we bring it all together.
The nervous system.
This is the true nervous system of modern aviation.
PBN.
Performance-based navigation. The ECQB exam leans intensely on PBN specifications, error monitoring, and terminology.
The absolute core concept of PBN, the philosophical shift you must understand above all else, is that PBN is not sensor-specific.
What does that actually mean for the pilot in practice?
In conventional navigation, you tune a specific VOR frequency and you fly the line generated by that specific VOR. You're flying raw data from a single sensor. In PBN, the aircraft's computer, the flight management system, FMS, takes raw data from the GNSS, the IRS, the DMEs, and the VORs. It mathematically blends and integrates all of them to produce computed data, a single, highly resilient position solution.
Wow.
PDN doesn't care which individual sensors are working or broken as long as the computed data meets the required performance standard.
There are 3 components that make up TBN, right?
The NAVIDE infrastructure, which is the physical satellites and ground stations, the navigation specification, which defines the rules and accuracy required for a specific block of airspace,
And the third?
and the navigation application, which is how the aircraft actually executes the procedure.
And the performance requirements themselves can be remembered with the acronym CIAF. Continuity, integrity, accuracy, and functionality. Availability is sometimes added, but CIAF covers the core.
That's a good way to remember it.
But the real meat of the PBN exam questions comes down to a battle of acronyms. RNAV versus RNP. Area navigation versus required navigation performance. If I am staring at a multiple choice question, what is the single most important distinction between the two?
The exam will test this relentlessly. The defining difference is that RNP requires onboard performance monitoring and alerting. RNAV does not.
I like to think of RNAV like driving with an old paper map. You can navigate anywhere, but if you drift off course, the map isn't going to yell at you. You might not realize you're lost until it's too late.
Right.
RNP is like driving with modern lane keep assist. The moment your tires touch the painted line, the steering wheel violently vibrates. It actively alerts you.
That is a brilliant way to conceptualize it. An RNP system constantly calculates its actual navigation performance, its ANP.
Actual navigation performance.
This is essentially the system's estimated position error. The system continuously compares this ANP to the required navigation performance, the RNT assigned to that airspace.
So if I'm flying into a congested airspace that requires RNP1, my aircraft needs to be within 1 nautical mile of the digital center line 95% of the time. My required performance, my RNP, is 1.
Your actual navigation performance, your ANP, must always remain smaller than your RNP.
Or else it alerts.
Exactly. If your ANP grows larger than the RNP, meaning your estimated error is greater than the allowed limit, the RNP system will trigger a major alert in the cockpit within 6 to 15 seconds. An RNAV system cannot do this. It just degrades quietly.
ANP must be smaller than RNP. The syllabus then breaks down how the system calculates these errors into something called total system error, or TSE.
Yes, TSE.
And it states that TSE is the geometric sum of 3 things: path definition error, PDE,
Yeah,
flight technical error, FTE, and navigation system error.
that's the formula.
So PDE plus FTE plus NSE equals TSE. Let me push back on this, though.
Okay, push back.
Why do we need 3 completely different acronyms for being off course? If the plane is 50 meters off the line, why does the syllabus care how we categorize those 50 meters?
Yeah. Because it dictates accountability and monitoring. It tells us exactly who or what is responsible for the error.
Oh, I see.
Path definition error, PDE, occurs when the digital route loaded into your FMS database is slightly mathematically different from the actual intended route over the ground. It is a database coding error.
So it's baked in.
Yes, it is considered mathematically negligible, and critically, the pilot and the onboard systems cannot monitor it. You simply have to trust the database integrity.
So PDE is the database's fault. Nobody in the cockpit can fix it. What about FTE?
Flight technical error, FTE, is the physical flying error. It is the inability of the pilot flying manually or the autopilot to keep the aircraft exactly planted on the digital line presented on the screens.
And who monitors this?
The flight crew monitors it by cross-checking their instruments and following strict standard operating procedures.
So FTE is the pilot or the autopilot's fault. We monitor that, which leaves NSE.
Navigation system error, NSE. This is the difference between where the aircraft's computers think the plane is and where the plane actually is in physical space. It is a sensor and calculation error.
And who watches that?
The RNP system itself monitors this, which is exactly what we just talked about, comparing the computed ANP to the RNP.
That makes total sense.
Yeah.
PDE is the database, FTE is the pilot or autopilot, NSE is the computer. The RNP system watches the NSE, the pilot watches the FTE, and nobody can watch the PDE.
He's got it perfectly.
That brings a lot of clarity to a very dry, jargon-heavy part of the syllabus. Now let's talk about where we use these different PBN specifications. The numbers change based on the phase of flight.
In vast oceanic and remote airspace, we use RNT4 and RNAV10. A key regulatory point for the exam is that flying RNAV10 in oceanic airspace explicitly requires the aircraft to have 2 independent long-range navigation systems on board, typically 2 independent inertial navigation systems.
Then as we get closer to land, into the en route phase, the digital corridors tighten up. We use RNAV5 and RNP2.
Yep.
Then we drop into the terminal, arrival, and departure phases, the SIDs and stars. And we tighten up even more to RNAV1 and RNP1.
What do all of those phases, oceanic, en route, and terminal, have in common regarding the type of guidance the computer provides to the crew?
They are all strictly limited to linear lateral performance. The boundaries of the digital corridor remain perfectly parallel no matter how close you get to a waypoint.
Right.
But when we finally transition into the approach phase, PBN accommodates both linear and angular laterally guided operations.
This is where we need to clearly distinguish between LNAV and LPV approaches. Let's start with LNAV, or LNAV VNAV.
Okay.
These are linear. They're classified as Type A approaches, meaning the minimum descent altitudes are generally above 250 feet.
And LPV, localizer performance with vertical guidance.
LPV is angular. As you get closer to the runway threshold, the digital corridor narrows, becoming more and more sensitive, acting exactly like an ILS localizer and glide slope. It allows you to fly down to much lower minimums.
And to fly an LPV approach, You absolutely need that final approach segment data block, the FAS data block,
Mm.
which is updated every 28 days via the global AI reg cycle.
Exactly.
Without an updated FAS data block loaded in your FMF database, you cannot fly the LPV.
That generates a very common exam scenario. An airline has two identical A320s, but one can fly LPV approaches and one can only fly LNAAV.
Why? Because the older one doesn't have the avionics capable of processing the FAS data block.
You nailed it. Now, I want to give you a golden rule of thumb for navigating the PBN exam questions.
Give it to me.
If a multiple choice answer links PBN together with ILS or MLS, the microwave landing system.
I know this one.
Mm.
It is universally 100% an incorrect answer.
Yes, it is.
ILS and MLS use ground sensors to create physical radio beams in the air. PBN uses computed data and digital databases. They are fundamentally different concepts in the eyes of the syllabus. Never mix them.
To wrap up PBN, you need to recognize a few specific system functions. The ARN's 424 path terminators, these are the underlying computer codes that translate government-published procedures into the FMS database.
The exam will test you on things like RF, which stands for radius. To fix this code, allows the aircraft to fly a mathematically perfect constant radius turn to a specific waypoint.
Right.
Or FRT, fixed radius transition, which manages the sweeping turn between two high-altitude en route segments. And you also absolutely need to know the navigation display, the ND modes in the cockpit.
The standard Airbus and Boeing ND modes are M8 or ARC mode, VOR or ROSE mode, APP or ROSE LS for ILS approaches, and plan mode for reviewing the route structure. Knowing what information is displayed in each of these modes is guaranteed to earn you points on the exam.
Let's zoom out and recap this incredible journey through the syllabus.
It's been quite the ride.
We started with the absolute basics, interpreting the physical swing of a VOR radial on a 5.HSI, figuring out our orientation from a single ground beacon, drawing out reciprocal headings on scratch paper.
Yeah.
Then we moved to space, looking at how atomic clocks calculate pseudo-range and how SBA systems like IGNOS can warn an entire continent of a satellite failure in just 6 seconds.
We synthesized all of that legacy and modern tech into performance-based navigation, where the aircraft integrates every sensor available to mathematically guarantee its position, constantly calculating its total system error, and actively alerting the crew if it strays outside the required navigation performance.
Mastering this material isn't just about passing the ECQB 2026 exam. It's about fundamentally understanding the nervous system of modern aviation. You aren't just learning how to read a dial. You are learning how a 300-ton aircraft knows exactly where it is in a three-dimensional void.
The transition to PBN is allowing air traffic control to pack aircraft tighter and tighter together in the sky. We are relying entirely on these invisible, mathematically perfect digital corridors to maintain separation and safety.
Which brings up a really provocative thought to leave you with. If our entire navigational infrastructure, our ability to safely fly thousands of aircraft simultaneously over oceans and continents, is now utterly dependent on a handful of atomic clocks floating in space.
Clocks that we know are vulnerable to solar storms, atmospheric interference, and increasingly intentional military-grade jamming.
Exactly. Are we designing an airspace that has outgrown human capability? If the satellites go dark and the screens lose their perfect digital lines, have we packed the sky so tightly that it's no longer geometrically possible to fly manually using the old ground beacons? It's something to think about the next time you dial in a VOR frequency. Keep studying, trust your instruments, and we will catch you on the next deep dive.